Hello, everyone. And I'm sorry I cannot speak Italian, so I will speak English. And thank you so much. I'm very happy to be with you, with all of you. Thanks to the Balzan Prize to Michael, which allow me to develop my research on exoplanet detection and characterization. And I'm a postdoc at University of Liège in collaboration with MIT in USA and the Canary Island, the Institute of Astrophysics of the Canary Island in Spain, in the context of Speculoos project. Speculoos that we will see later. So I'm going to talk about exoplanet detection or orbiting around small star, or I can say beautiful star. I will say why later. So everyone knows this is our solar system, okay, with the sun and rocky planet, Mercury, Venus, Earth, and Mars, and giant gas planet, which are Jupiter, Saturn, and Neptune. So, of course, that gas giant planet cannot support the life, or cannot support the liquid water on its surface due to the because the surface of a giant gas planet are dominated with HO2. To search for another planet with life condition, we should to look to the rocky planet exist in the habitable zone of the star, like our beautiful planet or blue planet, which is the Earth, okay, with the water, okay. Water is an element which is very important for life, else we cannot exist. So let's go far away. The first exoplanet was discovered in 1995 by Didier Queloz and Michel Mayor, okay? This exoplanet is a giant planet, it's a big planet around Sun-like star, which is the mass of this planet, it's around 0.5, a half of Jupiter mass, okay? And with an orbital period of 4 days. That means that the planet is very hot, okay? And this kind of planet named hot Jupiter because it is close to the star. And of course, on 2019, after 25 years ago, they got a Nobel Prize in physics, which is something very, very exciting. After that, okay, in 2019, we have first planet discovered around Sun-like star, but for now, we have 5,500 exoplanets have been discovered. There's a lot of planets that we have for now. And thanks to Kepler, TESS, CORO missions, space missions, and not forget, of course, the ground-based facilities as WASP, HATS, and a lot of projects have been detected. So this diagram represents all the planets that we have been discovered. The x-axis represents the orbital period of the planet in days, and the y-axis represents the mass of the planet. So we can see our solar system planets, the gas and the rocky planet, and here is all exoplanets that we have discovered. And we can see easily, for example, here, It's like giant planet, okay, but it's very hot. So they are this kind of planet named hot Jupiters, okay, and far away named warm Jupiters, okay. And if we can see here again, in the bottom, we can see the super Earth, the mini Neptune. So a lot of kind of planet appear. So our solar system is not unique, okay? There is a lot of kind of system. So as I mentioned, so our galaxy, or Milky Way galaxy, we can see a lot of stars, about between 100 and 400 billion of stars. Okay, if each star has only one planet, so we can have at least 4 billion of planets. Note that some stars has 4 planets, 7, 2, so we will have at least a lot of planets. And we are somewhere here, okay? It's just a little dot. So our solar system exists in this small dot. So we are nothing in our galaxy, okay? So how we can detect exoplanets? This is the question. So if we consider this lamp as find that a lamp is a planet, okay? And if we place it around its star, it's impossible to see directly the planet, okay? Because the star is very brighter, 1 billion times than the planet. So how we can detect them? We can use indirect methods. One of them most useful is the transit method, okay? We wait until the planet passes in front of the star, and in that time we measure the star luminosity, okay? And just to show you the principle of the method, so when the planet passes in front of the star, we can see a small tip of the luminosity of the star. That means that something is passing in front of the star, okay? And this, which means light curve, the transit light curve, we can analyze this shape to constrain the physical parameter of planet and of star itself, okay? This method cannot be only used for the detection, but we can go far away. We can use it for atmospheric characterization of such planets, okay? The idea is we can observe this transit, okay, in different filter or in different colors, if you want. And each color can give us an information about the atmosphere of the planet. And in that case, we can identify the molecule in the atmosphere. This study is very, very complex, and we need the huge observatories, okay? Oh, no, sorry. This, when we observe a transit in different colors, okay, we can identify the molecule on the atmosphere of the planet. This names the spectra or the spectrum of the exoplanet. And we can identify the water, for example, methane, ozone, a lot of molecules that we can identify it. And but of course, as I mentioned, that we need a huge observatories because, as you know, that the atmosphere is very thin, it's very small compared to the radius of the planet. So we need a very, very good precision on the measure. So we can use James Webb that was launched by NASA 1 year ago, or ELT that will build in Chile or TMT that will install in Hawaii. This is a good example that we have. Okay, James Webb observation. We observe the transit depths, okay, in different color, and we can identify which molecule. And here is WASP 39b is an exoplanet. It's a hot Jupiter, okay, and we can identify a lot of molecules, including CO2, water, etc. This is a very exciting result. So we will go back a bit to our solar system, our nice system. So this is the sun. Just I would like to compare the size of the sun, okay, and our planet. So our Earth is here, so it's too small in front of the sun. The sun is really huge, okay? But if you compare our sun with other stars, which means giant or super giant, super red giant or blue giant, our star is like a small point, okay? Let's compare our sun with other star, which is named small stars, our beautiful star, okay? It's the ultra-cold dwarf star. This is what we are following using our project, Speculoos project. Why small stars? In our galaxy, we have around 50% of the population in the solar neighborhood. So we have a lot of this kind of star, okay? Second thing, that if we look for the transit depths, if you remember very well, if we have a sun-like star with a small planet like Earth, we will have here a small depth, which means that it's very challenging to see it, okay? But with a small star, with a small planet, we can see a depth transit, which is very easy to observe it with the ground, of course. Second thing, that if we search for life outside of solar system, we should to look for the planet existing in the habitable zone of the star, okay? And habitable zone of the star it depends on the star itself. Due to the low mass star has a very low luminosity, so the habitable zone should be closer to the sun, to the star. So, for example, the Earth exists in the habitable zone of our sun, and it make one tour in 1 year, okay? One period. But for M stars, the habitable zone planets exist in around, we can have the orbital period in a few days, okay? 6 days, 10 days. That means that we will have a lot of transit each year. This is very important. The last thing, or another very important thing, that this kind of system orbiting low mass star are very important for atmospheric characterization using our current facilities like James Webb, ELT, and so on. This point motivated us to develop our project. Not that one, sorry. This is Speculoos. But that one, Speculoos project, is searching for habitable planet, okay, eclipsing ultra cold stars or low mass stars. The observatory consists with 2 observatories in the hemisphere in the south and the north, okay, with 1 meter class telescope, optical telescope, in collaboration with a lot of institutes, University of Liège, MIT, Cambridge, University of Bern, and University of Birmingham. And the idea here is to search for a rocky planet around M stars or around low mass stars. So here is the globe, okay? I would like to show you where we have the observatory. The Southern Observatory, or Speculus South, exists in Chile, okay? And we have 4 1-meter telescope already installed and already operational. We have one telescope for Speculus North in Tenerife, or in Canary Island in Spain. And additional, we have TRAPPIST, which is also a project installed by Liège in Chile in 2010. TRAPPIST North is the twice of TRAPPIST South, but in Morocco, and SANTEX in Mexico. But TRAPPIST North and TRAPPIST South are the small telescope of 60 centimeters of diameter, and Speculus, SANTEX are 1 meter class telescopes. So here is Chile, okay, and we have VLT, Vista in GTS, and we can see our observatory in Chile, and this is our 4 telescope. Named for each one has a name, okay? Io, Europa, Ganymede, Callisto is the name of the Jupiter's moon. And the northern hemisphere, we have only one, and of course that we searching for the funding for other telescopes. And this Artemis is the name of the telescope, and next year we will install a new one for Speculus North. That is very good. And, well, this is one of the results that we have. Is one exciting system have been discovered is TRAPPIST-1 system. So the TRAPPIST-1 is the name of the star, okay, which is discovered by TRAPPIST South in Chile. The small telescope is a prototype on Speculus North project, Speculus project. TRAPPIST-1, it's a very small star with a mass of 8% of the sun mass. So it's very low with the effective temperature of 2,500 compared to the 6,100 of the sun. So around this star, we have 7 rocky planets, not only 1, not 2, but 7 rocky planets. And all of them have a size of the Earth, okay? And so this is the facility, because we use also Spitzer, is the NASA. We use the VLT, we use a lot of projects to confirm this nice system. And also, in that, when the day discovered is out, Google also changed the logo. It's very exciting. So, and we have 3 planets in the habitable zone of the star. That means that this planet can have a liquid water on its surface, which means life, okay? But we are not sure. We have to observe each planet and to study its atmosphere and to see if we can identify the molecule, including azote, water, etc. This is the last slide. So we have a lot of data from James Webb Space Telescope for this system, because it's an exciting system for atmospheric characterization. We have a lot of transit for each one. We have the occultation. Occultation, when the planet pass behind the star, the transit when the planet pass in front of the star, the occultation when the planet pass behind of the star, we can learn also a lot of things from the planet, because in that case, when the planet pass behind the star, we can see the light of the planet itself, because the planet can reflect a small things of the light, and in that case we can constrain the equilibrium temperature of the day side of the planet. This is very important. So and we will waiting for the result, and we hope to find something very good. And to search for life, of course, that as we know that we need a huge observatory. And James Webb is already here, but of course to go far away in the spectrum, because James Webb can observe until 28 microns, so it's in infrared. But Origin Space Telescope will go far away. That means that we can identify a lot of molecules in the atmosphere. So Origin Space Telescope is one the objective of that project is to identify the biosignature. I finished before. The biosignature in the atmosphere, which are the ozone, HO2, dioxide, are very important molecule to find in the atmosphere of any planet. And this telescope will be launched by NASA in what I learned about, it's in 2035, so in 10 years or more. But it's a very huge observatory. Right, and that's it.
Do you take questions?
Yes, sure.
Professor De Bernardis, se vuol governare lei l'eventuale discussione.
Ci sono domande per il nostro amico.
Sì.
Prego.
First of all, a nice compliment for the nice presentation, okay? Oh, nice presentation and our compliments. Now, what would be quali sarebbero veramente le indicazioni che c'è la vita? Cosa intende cosa deve misurare per dire qui c'è la vita?
So the question is, what do you need to measure in order to state for sure that there is life in that planet?
This is a very good question. Thank you.
Una bella domanda.
Yes, to make sure that there is an indication of life, just indication is not life itself. It can be life, but we can see just an indication. We should to find the biosignature molecules, which are that I mentioned, HO2, ammonia, water, ammonia, CO2, okay, dioxide carbon, and the methane. And this is, if we find all of them in one atmosphere, this is maybe an indication. But this planet should be in the habitable zone of the star. This is first things. And it should be a rocky planet. If it's gas, we cannot search for life in a gas planet. I hope that I answer.
Yes. Altre domande? Prego. He's asking, è completa la domanda?
Nella nostra vita c'è ossigeno, CO2, eccetera, ma nessuno ha stabilito che ci sia una sola forma di vita, la nostra. Qual è il criterio di vita che voi assumete?
Okay, so the question is, when you say life, how do you define it? Because the suspect is that our life is not the only one possible. So that's the question.
It's a very big question. And we're still searching for the answer. When we say life is not for us, for example, it's just a bacteria, for example, or anything can live, okay? This is what we mean by life. And, well, if we suppose that we found a planet with life condition, for example, as I mentioned, the TRAPPIST-1 system is far away from us, 40 light year. 40 light year is very, it's very far away, okay? And if you suppose that we have a good planet there and with the life condition, and if we plan to go there, so it's just another dark question. So how we can go if we find a planet? A good planet, a good planet, that is a good question. So let's ask Elon Musk for that.
So you answered based on
yes,
thinking to carbon-based life.
Yes.
That's what you're doing.
Yeah,
but the question was, you mean, a bit more wide. Imagine there is based life not based on carbon. So in that case, well...
We don't know.
Okay. Ci sono altre domande? Prego.
Compliments for your exposition. And I ask a question. Which time is the end of the research? The end. And after, if I want to go, not with my car, what I do for go in another planet, if I hope this is possible to life? Excuse me, please.
Wow.
Thank you very much.
Fantastic question. Yes.
Fantastic
Go
question.
ahead.
To go outside of the solar system is not easy at all. Just to do the moon is not easy. So it's a lot of money to spend. And in particular, if we plan to go, for example, to the edge of the solar system, it's something crazy. So, right now, but outside of solar system, it's another story. I don't know.
That's a good answer.